Hi everyone, we're still on Unit 1, Functions and Relations. We are in Section 2 on the second chapter in Section 2. That, of course, is Chapter 3, and we're talking about polynomial functions. So there's a couple of curriculum outcomes here. Okay, we're going to demonstrate an understanding of factoring polynomials of degree greater than 2, but less than 5. Okay, so now we're going to be, you know how you factored x squared plus 5x plus 6 or something like that. Okay, now we're going to be expanding our skills of factoring into things like x to the 5th plus 4x to the 4th, that kind of stuff. Okay, and we're going to be able to graph and analyze polynomial functions. Again, limited to degree 5 or less. Okay, so a little preamble. Polynomial functions can be used to model different real-world applications from business, profit, and demand to construction and fabrication design. Okay, many calculators use polynomial approximations to compute function key calculations. Okay, we're going to use the ideas presented here to factor equations for exponents higher than 2 and use those answers to solve a variety of problems. Okay, the checklist for this chapter, you've already done the pre-assessment for Section 2, so we don't have to worry about that again. Okay, there's 4 parts to this, so characteristics of polynomials, the remainder theorem, the factor theorem, and then equations and graphs of polynomial functions. Okay, of course, when you're done the 4 videos and the practice for them, then you have a polynomial functions review, which is a formative assessment, okay, not for marks. Okay, then you have a polynomial functions curriculum view, which is a summative assessment, so is for marks, and then you'll have a chapter quiz again. Okay, so let's get started. Okay, part 1, characteristics of polynomial functions. Now, we've been working with polynomials for a really long time. We just haven't really called them that for a while. So all the stuff like x squared plus 5x plus 6, that was my example earlier. Okay, so that is a polynomial. Okay, x plus 2 is a polynomial. Okay, so we've been doing these a long time. Now, a polynomial really is any function that can be written like this. Now, you look at that and you're like, what on earth is that? Okay, so we have some coefficient to timesing x to some power of n. Okay, then a different coefficient, okay, and then a different power of x. Different coefficient again, different power of x. Okay, and we just go, usually polynomials are in descending order. Okay, so x is a variable, n has to be a whole number, right? We have to have whole number exponents for these. So a few examples. So 2x minus 1, okay, that's called a linear polynomial. Linear. Okay, x squared plus x minus 6, that's called a quadratic polynomial. Then we have these bigger ones, x cubed plus 2x squared minus 5x minus 6. That's called a cubic. Okay, remember the degree of a polynomial function is the highest exponent on the x anywhere in the equation. Usually we write them in order from biggest to smallest, but not always. Sometimes we try and just see if you're paying attention. Okay, so polynomials are named for the highest exponent, for the degree exponent. Okay, so if the highest exponent is 0, okay, that means there's no x's, which means it's a constant function. Okay, if the highest exponent is 1, it's linear, 2 is quadratic, 3 is called cubic. Now, 4 and 5, the 4 is quartic and 5 is quintic. But usually after 3, we just kind of say, hey, it's a degree 4, a degree 5 equation. Like, so you can name them either way. It really doesn't matter. Okay, remember the leading coefficient is the coefficient that contains the highest exponent. So up here in this one, okay, the degree term is 3. So the coefficient on that is a 1. Remember, there's a 1 in front of the x, so that would be the leading coefficient. Okay, so that was way up here, guys. Okay. Now, again, the constant term is any term that doesn't have x in it. Okay, so I want you to consider this particular polynomial. Okay, so x cubed plus 2x squared minus 5x minus 6. So there are 4 terms here. Okay, remember each term is separated by a plus or a minus sign. Not a big deal. Okay, so there's 4 terms. Okay, the degree is the highest exponent. So this is degree 3. The leading coefficient then is the number in front on that particular one. So the leading coefficient here is 1. Okay, and the constant term is the guy that doesn't have x on it. So the sign goes with, so that is minus 6. Remember, the constant term is important because that is always going to be the y-intercept on the graph. Great. Okay, so now we have a different example. Ooh, look at this one. Tricky, tricky. Okay, this one is not in order. Okay, and we do see those every now and then, so you have to pay attention. So there's a 7, then an x to the 3, x to the 4, and x to the 2. So x to the 4, that's the degree term. Okay, so the degree is 4. That's the highest exponent. The leading coefficient on that then is -5, and the constant term out here, that's plus 7. Okay, so the y-intercept on this graph would be plus 7. Awesome. Okay, so there are, of course, our rules about what type of functions are actually polynomials. Okay, it's usually easier to say what a polynomial isn't as opposed to what it is. Okay, so things that are not polynomials. Okay, any expression containing, so roots of variables. Okay, those are bad. Okay, absolute values of variables. So absolute value of x, that would not be a polynomial. So a root x would not be a polynomial. Okay, negative or fractional exponents. So if you have something like this, x to the -2. Okay, no, that's a bad one. Or even x to the 3/2. That doesn't work. Not polynomials. Okay, variables in the denominator. So if we have something like 1 over x, okay, that is not allowed. Now remember, these two are related because a negative exponent just flips the variable down to the bottom. So really those are saying the same thing. Okay, and then non-real coefficients. So if you have something like this, square root of -1 x squared, okay, this just doesn't exist. So if it doesn't exist at all, then it can't be a polynomial function. Okay, so that's the idea. So example 1 is just, I gave you a whole bunch of polynomials and you just tell me whether they're polynomials or not. Okay, we're going to circle the part that makes it not a polynomial. So -4x cubed, that looks good. Oh, the 3/2, that's bad. Okay, so this is a no. You can't have a fractional exponent. Okay, so 3x to the 4th, that part looks good. Oh, look, negative exponent. Okay, so then no. And as long as one of the terms has something wrong with it, then the whole thing is not a polynomial. Okay, so let's look at this guy. So x to the 4th looks good. This x cubed looks good. Root 6x squared. Now look at how that root doesn't go over. So root 6 as a coefficient is just fine. So this guy is a polynomial. Yes. Okay. This guy here, though, root 3 x to the 5th, see how that root expands over the variable? So now that is a no. Okay, we can't have that. Now, e is really tricky because you look at d and you think the e might be the same thing. But funny, because look, the x cubed, the 2x squared, and the 8, those are all fine. Okay, if you look at this, though, this reduces to root 3, and what's the square root of x to the 4th? Remember, that's just x squared. So this one actually does count as a polynomial because that root cancels off the variable part. Now, lucky for us, we don't have a lot of those, but you just should be aware that that is classified as a polynomial function. Okay. Here we have an x on the bottom, so that's a no. Here we have, ooh, look, the square root of a negative, so that's a no. Okay, you can't square root -5. And yeah, just nope. Okay, it doesn't matter what's going on with the variables there. The coefficient isn't real, so it's not a polynomial. And then this one has an absolute value, so that is a no for that one as well. Okay, so again, these are kind of examples and non-examples of polynomials. Moving on. So, characteristics of polynomials. Okay, so this little chart, there's a lot of information in this, and we're going to go over it just kind of quickly. A lot of this is common sense, but not all. Okay, so the first one, a degree 0 is a constant function. Okay, so remember, constant functions are just horizontal lines. Okay, the domain is everything. The range is just whatever the value is. So in this case, it's 3. Okay, because y doesn't go any higher or lower than 3. It's just 3 the whole time. Okay, so degree 1 is called a linear function. Okay, look, it has one x-intercept. Okay, that's pretty straightforward. Okay, and it goes on forever in both directions. So domain is an element of the reals, range is an element of the reals. Awesome. Okay, degree 2 functions, those are your quadratics, your parabolas. So your domain is x is an element of the reals. Okay, y is bigger than or equal to whatever that minimum point is. We can have quadratics that go upside down as well. So they can have maximum points. Not a big deal. There are 2 x-intercepts. Hey, look, degree 2, 2 x-intercepts. Degree 1, 1 x-intercept. And hopefully you're seeing the pattern there. Okay. Anyways, the parabola extends up into quadrant 2 and up into quadrant 1. Okay, so then a cubic function looks something like this. So check this out. Degree 3, 1, 2, 3 x-intercepts. Nice. Again, extending upward into quadrant 1 and downward into quadrant 3. Okay, the domain of this thing is everything. The range of this guy is everything. Okay, quadratic function of degree 4. So check this out. 1, 2, 3, 4 zeros, 4 x-intercepts. Okay, wow. Okay, so we have 4 x-intercepts on that one, degree 4. That's kind of nice. Now, look, this is saying 0, 1, 2, 3, or 4. We'll get into how that works later, but we are expecting 4 x-intercepts. Okay, the domain is x is an element of the reals. The range, you have to figure out that low spot. Okay, so it's going to be bigger than or equal to that. Again, the graphs extend high into quadrants 2 and quadrant 1. Okay, and then our last one, degree 5. Remember, that's all we're responsible for in Math 30-1. So there's 1, 2, 3, 4, 5 zeros. Okay, and we go high into quadrant 1, low into quadrant 3. Are you noticing a pattern with that? Hopefully you are. Look at all the odd degrees. So 1, 3, and 5. They all end up high in quadrant 1. The degree 1s always end up low in quadrant 3. The even ones, okay, 0 doesn't really count, but the even ones, they end up high in quadrants 1 and 2 on both of those. So it's just one of those patterns. Okay, we'll summarize them here on the next page. Okay, the previous page showed some very important things about polynomials and their graphs. So a super quick summary. Okay, positive even graphs. Okay, they always ended high in quadrant 2 and high in quadrant 1, and then they did a bunch of things in between, like a degree 2 just did that. The degree 4 one did this. Okay, really, it doesn't matter what the middle stuff does. The end behavior for a positive even is high in both quadrants. Okay, if you kind of do that, if you put your arms up in the air like the referee in football, hey, touchdown, woo. Okay, now a positive odd graph looks like this one. So it is low in quadrant 3 and high in quadrant 1. So it can do a bunch of this. Okay, odds, remember, have 1, 2, 3, 4, 5 zeros for this one. Okay, the cubic ones are exactly the same. There's just 3, 1, 2, 3. Okay, and it ends up high in quadrant 1. Okay, so we have positive evens high in quadrant 1, positive odds high in quadrant 1. That's interesting. We'll come back to that. So a negative even graph. Okay, so if you have negative x squared, remember that's a flip in the x-axis. So then the graph looks like that. So now we're low in quadrant 3 and low in quadrant 4. Kind of looks like a frowny face. So I guess this guy could be a smiley. Smiley, frowny. Okay, looks like a big frowny face. Okay, and again, even the, oops, okay, even the 2 to the 4ths and 6ths and stuff, they, okay, 1, 2, 3, 4. Okay, so a negative to the 4th also ends up as a frowny. Okay, a negative odd graph would be high in quadrant 2, okay, and then low in quadrant 1. Okay, so check this out. They're both low in quadrant 4. So if the function or the polynomial is high in quadrant 1, you know that it's positive. If either of them are low in quadrant 4, then you know that the function is negative. If they have the same end behavior, both up or both down, then you know it's an even polynomial. And if there's one of each, one arm is high and one arm is low, then you have an odd function. Okay, well, there'll be lots of patterns that we'll see as we go through this, so you will pick it up if you haven't already. Okay, so every time the graph crosses the x-axis, it counts as a 0. The number of zeros gives the degree of the polynomial. Now, remember on this page, I'm going to flip back here, remember how it said there are 0, 1, 2, 3, or 4 possible x-intercepts? Well, there doesn't always have to be 4. So look, a straight through, okay, sorry, I'll just read the thing. There are some different cases of zeros that will be discussed in great detail later, but for now, you just need to know that there's some shapes that mean a different number of zeros. So if you go straight through a graph, this counts as 1, 0, and that counts as 1, 0. Okay, so this particular thing, this would be degree 2. Awesome. Now, the funny thing is, if you have what's called a tangent point, like this, okay, so it just touches the x-axis, that actually could count as 2 zeros, 4 zeros, 6 zeros, 8 zeros. Okay, these are an even number of zeros. It's called a tangent point. Okay, and it represents 2, 4, 6, or 8 zeros. Usually questions ask for the smallest degree, so it's usually 2, but it can be 4, 6, or higher. Okay, so that's called a tangent point, and that can be on either side. Okay, so of the x-axis. Okay, now a point of inflection does something similar. It's just a kind of a squiggle, okay, on the x-axis. Now this particular point means that there are 3, 5, 7, 9. They're an odd number of zeros. Now, of course, odd, that's not straight through. Okay, remember over here, this was a straight through, and this was a straight through. So those are just 1 each. Okay, that 1 is odd, but higher odd numbers, 3, 5, 7, 9, they have this squiggle, that point of inflection. Okay, what that means is that that 0, let's say it's at -1, so if the 0 is at -1, the factor then is at +1, and it means that 0 happens 3 times. It's called multiplicity, and we're going to talk about it at near the end of this unit. But for right now, you just need to know that those shapes make different numbers of zeros. Okay, so example 2, match a polynomial function with its graph. Okay, so what I want you guys to do, match each function with its corresponding graph. Ooh, that was weird. Okay, with its corresponding graph, and identify some of the characteristics below to help. You don't have to identify all of these, but just these are some of the things that will help. Okay, so we want the type of the function, even, odd, end behavior, number of possible x-intercepts, whether the graph has maximum minimums, and the y-intercept. So all of these things can help when we want to figure out which equation would be the graph. So if we look at A, okay, so A, so the highest exponent is 4, so there's going to be 4 zeros of various types, okay, and oh, look, it's a negative. Okay, so that means the end behavior is going to be a frowny. So they're going to, because it's a negative to the 4th, both arms are going to extend low. So look, A, this graph, okay, that's an odd graph. Okay, hey, this one's even. Okay, but oh look, they both arms extend high, so that's not it. Okay, oh, look at this one. Both arms extend low. There's 1, 2, 3, 4 zeros. Okay, so that's our guy. This is D, graph D. Okay. All right, so B is a positive cubic. Okay, so that means we have the squiggle, and being positive, we're high in quadrant 1, low in quadrant 3. So, oh look, high in quadrant 1, low in quadrant 3. Okay, it's odd, so that looks like it could be it. The y-intercept is +3. Hey, y-intercept is positive. So yeah, this guy is graph A. Awesome. Okay, looking at C. All right, so it's a negative to the 5th. So that's negative odd. Okay, so that's going to extend low into quadrant 4, high into quadrant 2. Okay, it's looking like this guy. Now, it can't be this. The only other choice is B. It can't be this one because B is high in both quadrants. So this is an even function, which means C cannot be that graph. So C has to be this graph. So graph C. Okay, awesome. Well, there's only one left. D has to be graph B then. But let's just make sure. So it's positive x to the 4th, so that's a smiley. Okay, so that extends high in quadrants 1 and 2. Okay, the y-intercept is negative 12. Yeah, that looks like it could be negative 12. Okay, 4 x-intercepts, 1, 2, 3, 4. Okay, that's perfect. Did we check the intercepts on C? 1, 2, 3, 4, 5 x-intercepts. Yeah, look, 5 x-intercepts. Okay, degree 5. So, yeah, we got it right. So, graph D, then A, then C for C, and letter D is graph B. Awesome. Moving on. Okay, so an application of a polynomial function then. Okay, a bank vault is built in the shape of a rectangular prism. Remember, that's just a fancy word for box. Okay, the volume V is related to the width in meters of the vault doorway by this particular function. Okay, W cubed plus 13W squared plus 54W plus 72. Okay, awesome. What is the volume in cubic meters of a vault if the door is 1 meter wide? Okay, so really all that wants is volume with the width of 1. So we put the 1 in for W, so 1 cubed plus 13 times 1 squared plus 54 times 1 plus 72. So you just type that into your calculator and you get 140 cubic meters. So the vault is that big. Okay, the door would be 1 meter wide. Awesome. Okay, so B, what is the least volume of the vault? Then it says, what is the width of the door for this volume? Why is this situation not realistic? Okay, we'll tell you what, we're going to graph this one just because we can. Okay, now when we graph this function, okay, it actually looks something like this. Okay, down and then way up, so this is 72. You're going to have to change your window to see something like this. Now, it makes sense that we can't have a negative width for the door. So all of this stuff down here makes no sense whatsoever. Okay, that's going to be not possible. So really our domain on this is W is bigger than or equal to 0. Now, that's the official domain because I guess you could have a doorway of 0.2 centimeters, but that's not realistic. Anyways, so right here at 72, that does exist. Okay, so that's going to be the least volume of the door because all the volumes go higher after that. So the least volume possible is 72 cubic meters. But no, it's not realistic because this particular vault wouldn't have a door. It kind of makes it a pretty useless vault. Okay, why is this situation not realistic? The width of the door is 0. Door is 0, which means there's no door, which means, yeah, you can never get in. Your stuff would be safe, but you'd never get it again. So, very, very bad. All right, moving on. Okay, so there's some key ideas here. Okay, polynomials. We talked about positive ones, polynomials always being high in quadrants 1, low in quadrants 3. Okay, so those work for both. Pardon me. High in quadrant 1 works for both odds and evens. Okay, so we talked about what makes a polynomial. The odd degree have the following characteristics. The graph extends down into quadrant 3, up into quadrant 1. Okay, if the graph extends up into quadrant 2 and down into quadrant 4, then the leading coefficient is negative. Okay, the y-intercept is the constant term. Okay, at least one x-intercept and up to a maximum of n x-intercepts. So n, of course, is the exponent, or the biggest exponent, the degree, if you will. Okay, the domain is x as an element of the reals. The range for odds is an element of the reals as well. There's no maximums or minimums because it just goes on forever. Even graphs are a little bit different. Okay, they have either smileys or frownies. Okay, so they both extend up into quadrant 2 and 1. Okay, so that means the leading coefficient is positive. If they're both down, so down in 3 and 4, then the leading coefficient is negative. Okay, y-intercept again is the constant term, and we can have up to the degree term of intercepts. Okay, these ones do have maximum and minimum values, and you just graph those to find them out. Oh yeah. Whoops, sorry, my bad. There's more at the bottom. Okay, so we're done section 1 here. I want you guys to practice. Okay, so this is chapter 3 in your textbook, so section 3.1, starting on page 114. Okay, so there's a few questions. You can do more. Okay, and these questions can be done right out of your textbook, or you can print the workspace card. Again, I encourage you to print the workspace card because then you can write all over the paper. Okay, don't want you writing in your textbook, obviously. Okay, remember the answers are in the back of your textbook, so you can check as you go. Okay, ask your teacher or email or text me, and we'll go from there. Thanks, guys.